Thank you. Extra, I'll just put it in here. All right, any others? Okay, so look, I mean, I'm sorry to walk in here and give you a quiz. Like, I get it, it's not fun, but here's the thing. I mean, it's one quiz. I'm going to drop at least one, okay? The more quizzes we have, the more I'll drop. So don't let this be like, oh man, I better go drop the class now. But you do have to be honest with yourself, you know, are you prepared? So I gave you 5 minutes to do these two problems because I believe to be successful in this class, you should be able to do those in 5 minutes. And, you know, with formula sheets especially, you should be able to do that. If you don't have the formula sheets, then, you know, yeah, you might be hung up on it a little bit. But, you know, a lot of times I hear students talk about, you know, test anxiety and, you know, I feel like I understand it, but I come into the test and then I'm like, well, this is like practice, right? We're trying to get ourselves into that mentality of being ready when we come into class. So bring your formulas every day, right? Bring your calculator every day. Bring your notes every day. Bring your homework every day. Because I could have very well have given you this quiz and said, you can use your homework. I could do that. And if you don't have your homework, you don't have your homework. So, you know, how many of you have jobs? Okay? All right? So I'm sure for your job you have like a uniform or you have certain things you have to take with you, right? Same thing here. This is your job. You have to come in here, you have to be prepared. The requirements are have your homework, have your stuff, have your formula sheets, be ready, okay? All right, let's go through these. This one right here is a product rule. So we have to first take derivative of x, which is going to be 1, and then times this, so just arctangent of 3x, and then product rule says plus derivative of this. And what is the derivative of arctangent of anything? 1 over 1 plus that thing in here squared. Okay? Burn that into your memory, all right? The derivative of arctangent of something is 1 over 1 plus whatever that argument was squared. And then you have to finish up. You're not done, right? What else now? You have to take derivative of 3x, which is 3. And you're still not done. You have to finish the product rule, x. Okay. I'll clean it up. Yeah, I guess I can clean up. What happens here? We get, that stays the same. This is 3x on top over 1 plus 9x squared. Okay. All right, that's it for that one. And then this out here, right? Okay. Second one, this is not a product rule, this is composition, right? So you have to take derivative starting with the outer function, and the outer function here is cosine. The derivative of cosine of something is? Negative sine of it. So we're going to be negative sine of this right here, right? Cosine hyperbolic of x squared times chain rule. Now the derivative of what was inside. Derivative of cosine hyperbolic is just sine hyperbolic. No, there's no negative sign there, right? And then take derivative of what's in there, 2x. Okay, that's it. It's always easier watching someone do it, right? All right, moving on. Today we're going to start some new material. Like I said, the projector's still dead, but we can survive without the projector. You're just not going to get some of the cool animations that I have. But I hope that by the end of the week we'll be up and running, all right, hopefully. If not, I'm either going to ask for a room change or I'm going to ask for them to provide me like a projector on a cart or something. The room change sounds good because then we don't have to smell this room anymore. But okay, we are doing 4.7 today. Antiderivatives. So you have already, like everything we've done up to this point, we introduced some new functions, right? And then we took derivatives. So we still haven't really done anything that would be technically considered anti-differentiation or integral calculus. We're about to step into the Cal 2 now. I realize that some of you saw some of this in Cal 1. So by a show of hands, How many of you did some antiderivatives in Cal 1? Okay, anybody not touch antiderivatives at all? It's okay, I just want to see. Anybody? You did not? You did not? Okay. So what I'm going to do is go a little bit faster through this than I normally would, because you have seen some of it. And you might be saying, no, slow down. But trust me, you're going to want this time later, all right? When we're trying to do something more complicated, you're going to want to have more time. So I think if I can get through this pretty quick, we'll be happy later. All right, so first, kind of like a definition. If we are given some function of x, then capital F of x is called an antiderivative of little f of x if the derivative of capital F of x is equal to little f of x. So this right here is a definition. We are defining this function called capital F, and it's called the antiderivative. Well, the antiderivative of little f. All right, so the only condition that is required to be able to call capital F an antiderivative of little f is that if you take the derivative of capital F, you better get little f. All right? So some examples of this. If I say little f of x is equal to 2x, then capital F of x equals x squared is an antiderivative, because the derivative of this is this, right? Now, that's not the only antiderivative. Can somebody give me another antiderivative of this? X squared plus 1 would have worked, right? Let me do that. Why don't I'm still going to call it capital F, but why don't I call it capital F subscript 2, and I'll call this one subscript 1. And I'm doing that because these are two different functions, right? So capital F subscript 1, x squared works. That's an antiderivative of this. This is also an antiderivative. Any others? Can you come up with a third antiderivative? X squared plus any number, right? All right, so pi, would pi work? If you wanted to get all fancy. Could I subtract a number? Right? Any of those would work. And what we're using is the idea that when you take the derivative of a constant, right, by itself, it goes away, right? So you're always going to wind up with that 2x squared. I mean 2x. Now, could I throw any x's into this, though? I couldn't, right? If I threw, if that was 7x, that would not work, because then I would have minus 7 in my derivative. So it looks like, it has to look like something, right? So this time I'm going to do capital F, but I'm not going to put subscript. It looks like a general answer would be x squared plus any constant, right? Now we have a technical name for this C. We call it later, we'll call it the constant of integration. But for now, just think about it as in you can add any number to this x squared and it would qualify as an antiderivative, right? Okay, so geometrically, here's what's happening. We have a family of functions, don't we? These all have something in common. They're all parabolas, right? And if we do plus 1, like if we look at this one and we graph it, we all know what x squared looks like? Okay, so x squared looks like this. That would be capital F1, right? What would capital F sub 2 be? That one just moved up 1, right? It would just be this whole graph moved up 1. And then what about plus pi? Well, it would be that one moved up pi, right? So whatever. They all look almost the same. They're just vertical translations up and down, aren't they? Minus 7 would bring it down. So all of these graphs would satisfy being an antiderivative of this. So we don't have a unique answer. Do you all see that? We have a family of answers, but they all have similar characteristics. And the characteristic that they have is that if somebody picks a point right here, let's just pick a point, let's call it A. If you take the derivative of any of these at A, what would you get? So take the derivative of that, you get 2x, right? Now plug in A, what would you get? 2a? Okay, take this, take the derivative. You get 2x, plug in A, you get 2a. This, same thing, right? Derivative. So that means geometrically, if I go to A and I go to, let's say, this first one, and I try and find the slope of the tangent line right there, it's the same as going to this curve and finding the slope of the tangent line. It's the same as going to this curve. In other words, all of these are parallel. The entire family shares parallel derivatives. Does that make sense? Okay. Now, if you change the shape of the parabola this way, then you're going to screw things up, right? And that's why we can only add a constant. We can't put numbers in front of x squared. That changes things, right? Okay. So I guess the key idea here is that when we are talking about antiderivatives of functions, we get families of functions as opposed to a single function, right? Okay, so naturally what we want to know is, what can we find the antiderivative of, right? If I start throwing functions up here, can you start giving me their antiderivatives? And we're going to find we're very limited as to what we can and cannot do, all right? So let's start with something very basic. I don't know if I should call this basic. How about some known antiderivatives? All right, how about this one? If little f is cosine of x, can you tell me what an antiderivative of that would be? Sine x, right? Not negative sine x, right? It's sine x, because when you take derivative of sine, you get cosine, right? So the antiderivative, or an antiderivative of cosine of x, is sine of x. Now, could we still do plus c? Sure. I mean, that still qualifies. In fact, for all antiderivatives, we always have plus c, always, because we're going to get a whole family. So this is a family of sine curves. They're all moved up and down. Take derivative of any of those, and you're going to get this. Okay, so that's a known one. How about the next one? How about antiderivative of sine x? So capital F of x. What would we need to take the derivative of to get positive sine x? Negative cosine x. Right? Plus some constant. So here we do have to account for the fact that when you take the derivative of cosine, you get a negative sign. So we have to put a negative in front so that it kills off that negative and becomes positive over here, right? What are some other things? You could basically think of all the trig functions, think of their derivatives, and then go backwards. So what would be, let's see, derivative of sine is cosine. We kind of got that one here, right? Derivative of cosine is negative sine, so we kind of got that one here. Next one's tangent. What's derivative of tangent? Secant squared, right? So I could put secant squared x here, and I know that its antiderivative is got to be tangent x plus c, right? What about the other trig functions? Do you remember what the derivative of cosecant x was? Well, it's on a formula sheet somewhere if you don't remember it. It's negative cosecant x cotangent x. So I could put that here. If I'm trying to find the derivative of negative cosecant x cotangent x, then it would be cosecant x. And do you realize we could do this for all the trig functions that we know? Yes? You sure? You understand that? Okay, now I said things are going to get more challenging. So what about this then? I mean, this seems so trivial because the derivative of tangent is secant squared, right? But what about the antiderivative of tangent? What do you take the derivative of to get this? Not so easy, right? Not so easy. you see that? I mean, this is a pretty simple function, but its antiderivative is not something you know, is it? Like in Cal 1, you never took the derivative of anything and got tangent. Not something that they just provided you. We'll do it. We'll do that hopefully today. I'll answer this question. And you could actually do that for several trig functions that you just can't find them. Secant x. If it was secant squared, it'd be tangent, right? But it's not. So cosecant x just by itself, what's its antiderivative? I don't know, right? It has to be exactly negative cosecant cotangent, then I can go backwards, right? All right, let's try something else. Let's step away from the trig functions for a little while. How about this? So these were, I said, some known ones, right? Yeah. These are the known ones right here. And then there was some more that we should know from our Cal 1 class. These right here are big question marks, right? But here are some more that we should know. E to the x. E to the x, right? Plus a constant. There's another one that you should know. 1 over x. Natural log. Okay, so right now, your ability to find an antiderivative is directly related to what you know already about taking derivatives, right? Mm-hmm. That's the only real attack that we have, all right? But as you're going to see, we're going to start now developing some more systematic approaches for functions that look a certain way, and then we can try something else. Okay, so these are the known antiderivatives. And there is a table in 4.7 that summarizes this, all right? Okay, so let's try something else. Let's take a look at an example here. How about if I give you little f of x equals x to the 4th power? Then what would its antiderivative be? So we remember in Cal 1 that when you took the derivative of a power function, if you had x to a power in Cal 1, the derivative was that, right? That was the good old power rule. Power comes down, subtract 1 from the power, yes? Well, we're going to try and go backwards now. So if we're going to go from x to the 4th and we've got to go back to capital F, then if this is a power function, then what should happen to the power? It should go up, right? Because it has to come down the other way. So it's going to have to go up. So I know that I'm going to have x to the 5th. But that's not quite it, because when we take the derivative of this, the 5 comes out. And I don't have a 5 here. So I'm going to divide by 5. Or if I'm going to say it a different way, I'm going to scale it by 1/5. Okay? Dividing by 5 is the same as multiplying by 1/5. Yes? So if I put a 1/5 out there, the 5 comes out, this turns into a 1, power comes down, we've got this, right? And it seems like we could probably do that for any power. Do you agree? And that actually is going to turn into our first rule. So let's try something else. How would this change the problem if I put 3x to the 4th? Oh, I forgot plus c here. That is an antiderivative, but this gives you all of them, right? It's a general answer. Okay, so how does that 3 impact things? Well, we know it's still x to the 5th, right? That's got to be x to the 5th. But when that 5 comes down, I need to end up with a 3, right? So what I'm going to do is kill the 5 and introduce a 3. So I'm going to multiply by 3/5. Right? The 5 will kill off the 5, and the 3 will just stay there. So you could just look at it this way if you wanted to. You could have just said, okay, when I'm trying to find that, I just put a 3, and then I do the same thing I did there, like a 1/5 x to the 5, right? Plus c, plus c. And then this right here would have given you that. So the constant comes for the ride. Just like in Cal 1, when you had a constant in front of a function, the constant came for the ride. When you do antiderivatives, the constant will also just come for the ride. All right? All right. Maybe we can come up with a rule. Maybe we can generalize this now. Maybe there is a power rule for antiderivatives. Maybe there is. So let's try it. If we had little f of x was x to any power, then the general antiderivative of this, what are we going to have to do to the power? We've already talked through this. We're going to add 1 to it. So why don't I put x to the n plus 1, right? But just like before, that n plus 1 is going to come out in front, and I need to kill it off. So what would I multiply by out here? I could either divide by n plus 1 or multiply by 1 over n plus 1. That's the same thing, isn't it? And then add a constant to this. And that indeed is the power rule for antiderivatives. So now you have a power rule like you had in Cal 1, you had a power rule. Now for antiderivatives, we have a power rule. But there's one problem with this power rule. There's one issue. It doesn't work for one particular value of n. What value of n? What value of n would I have to put here to make your formula go crazy? Negative 1. If n is negative 1, look what happens here. Negative 1 plus 1 is 0, and you get division by 0. And you're not allowed to have division by 0, right? So this formula only works for n not equal to negative 1, right? So then we say to ourselves, crap, well, how do we deal with it when it is negative 1? So let's take a look at it. If n was negative 1, wouldn't that be that? Yeah. And isn't that the same as this? And didn't you just tell me what the antiderivative of that was? Natural log. So it turns out that we have a way of handling x to any power. This formula takes care of it as long as x is not negative 1. N is not negative 1. Here's the formula. And this takes care of it if n is negative 1. So we got all bases covered. So now if somebody gives you a function that has a power function and a power of x, you've got a formula. And this is the only formula we're ever going to get in this class to do antiderivatives. This is it. Everything else is going to be a technique. It's going to be something we try and hope that it works. All right? So this is, if you like formulas, this is the first one and last one for antiderivatives. Okay, now let's try this. And I'm going to throw you right into it, okay? I'm going to give you two examples here. First one. Let's say that little f of x is equal to square root of x plus 5 cube root of x minus 4 over the square root of x plus 9 over the 4th root of x cubed. I would like for us to find capital F, find the antiderivative of that. So, first thing, in Cal 1, when you took derivatives, if you had addition and subtraction between your terms, you could take derivative each one individually, right? With antiderivatives, it works exactly the same way, and that's great news. If we have separation with addition and subtraction, we do them individually. Now, when you look at these, are these any of the known antiderivatives or known functions? Sine, cosine, any of those things? No, right? But they are all powers of x, aren't they? So what I need to do first is rewrite them as powers of x. So I'm not going to find the antiderivative yet. I'm just going to rewrite the function. So square root of x is the same as x to the 1/2 plus 5, and then cube root of x is x to the 1/3 minus 4 over square root of x is x to the 1/2, and then plus 9 over, what's that? X to what power? 3/4. Quick reminder that if you have the nth root of x to the nth power, this is the same as x to the m over n. Back in college algebra, we talk about rational exponents. The whole reason we don't use radicals, or we kind of stray away from radicals in college algebra, they start teaching you this, is because they know in calculus you're going to need to work with the exponents as numbers instead of radicals. So this conversion is important here, right? Now I'm not quite there yet, because the formula that we have only handles x to a power, right? It doesn't talk about, like these two cases right here, the x to the power is underneath something, right? And the formula doesn't handle that. But fortunately for us, powers of exponents, I can bring that up, right? And I can bring that up, and it just changes the exponents to negatives. So I'm going to rewrite it one more time. The 4 is just going to sit out in front of x to the negative 1/2. And the 9 is going to sit out in front of x to the negative 3/4. All right. Is everybody good with the idea that we have 4 terms and each one of them has x to a power? And what about the 5, the negative 4, and the 9? Do we really care about those? They're just going to come along, right? When we find the antiderivative, they're just going to come with us, all right? So here we go. Let's get capital F. And I'm going to take this kind of a little slow on this first one. Okay, for the first problem, or the first term, the n we have, right, is 1/2. So the formula is supposed to be 1 over n plus 1 times x to the n plus 1, right? So if I was writing that out to show every little bit of detail, I'd go 1 over n, 1/2, plus 1, x to the n, 1/2, plus 1. And that would be the antiderivative of this one, right? And then I put what? Plus 5. And then I do the antiderivative of x to the 1/3, and now my n is 1/3, right? So I go again. Formula: 1 over 1/3 plus 1, x to the 1/3 plus 1, and I keep going. 2 more to go, right? Minus 4 is going to come along with me. And now I'm working on this one right here. And this time my n is the negative 1/2. So it's going to be 1 over negative 1/2 plus 1, x to the negative 1/2 plus 1. And I'm probably about to go off the screen here. Yeah, I actually am off the screen a little bit. What's the last one? There we go. I think I'm going to do that. Plus 9. I'm going to do it right underneath this. Plus 9, and then what? 1 over 3/4, negative 3/4, plus 1, x to the negative 3/4, plus 1. And then all of that plus c. Now, you could say that there was a plus c for each of these, right? But if all of these had constants added, then you could put them all together into one constant at the end, right? Okay. And now you get to show off your fraction skills. And I remember when I was first learning this, I was like, wow, I'm going to have to be doing constantly doing 1 plus a fraction. This fraction changes from problem to problem, but it's always plus 1, right? So you just have to get really good at adding 1 to fractions. And just as a reminder, if you have a fraction, let's say 5/7, and you add 1, what's the process? 5/7 plus, you just rewrite the 1 as 7/7. You just look at that denominator, add them up. So this would be 12/7, right? Okay. So for each of these, I'm going to assume you can do that. So we have, let's see, what's 1/2 plus 1? 3/2. Agreed? But what's 1/3/2? 2/3. It flips the fraction. So we actually get this right here becomes 2/3. And then x to the, well, we already did that, right? That's the same addition we had, and that was 3/2. So if you look, like this number and this number, they're reciprocals, aren't they? Like 3/2 here, the reciprocal 2/3 is here. All right, that took care of this. Now the next one, plus, I'm going to just put the 5 out here. And then what's 1/3 plus 1? 4/3, but 1/4? 3/4. X to the 4/3. And you'll start, trust me, you'll get fast with this after you do about, I don't know, 200 of them. You'll get quicker with it, all right? Yes, you could do that. But, I mean, just make sure that if you have a 5 out here, don't forget about it. Yeah. So -4. So, yeah, if you want to approach it that way, I'll do it on this next one. I could just do this first, right? Which is -1/2 plus 1 is 1/2. So out front is 1/2 flipped over. So 2. So 4 times 2, and then x to the 1/2. -3/4 plus 1? No, this would still be positive 2, right? Because you're doing these two added right here, so you're going to get a positive 1/2. Okay, what about this? This is 1/4, isn't it? So we're going to have the 9 plus 9. And then this power is going to be 1/4, which means out front is going to be a what? 4? The reciprocal of 1/4 plus a constant. And now you just want to put all your constants together, like 9 times 4. You want to go 4 times 2. You want to go ahead and multiply those fractions. And you get 2/3 x to the 3/2 plus, there's nothing I can do here but multiply that. And remember, it's like 5/1. So it's going to be 15/4 x to the 4/3 minus 8 x to the 1/2. And then plus 36 x to the 4th plus c. That's it. Now there's always good news in Cal 2. There's always good news, and that's when you're doing antiderivatives, you can always check your work, right? You can always check to see if you got the right answer by just taking the derivative. Now we'll see later, we don't have time for that in class to check check the derivative. But this one I think would be pretty easy to do. Let's just try and do it mentally. This comes out, right? 3/2 hits that and becomes a 1, right? So I have a 1 here, yes? And then I take 3/2 and I subtract 1 from it, which should leave me with 1/2. So that gives me that first term, right? This one, the 4/3 comes out, hits that. And when you do that, you should get 5. Okay, subtract 1 from that, you should get 1/3. Oh, this one works nice. Half of -8 is going to be -4, right? But check this out. When you subtract 1 from a half, 1/2 minus 1 is -1/2. And so you get, well, that right there. And then this one works also. Okay? So what do you think? So if we have a bunch of terms, right, separated terms with powers of x in them, we should just be able to manipulate the expressions to the point where they're all x's to powers and then just crank out the rule, right? So let's do another example. I'm just going to tweak it a little bit. And let's see if we can still do that same thing on this one. How about this? -3 root x plus 5x minus 7 over over x squared. So the biggest mistake that I see in a problem like this is that a student will say, okay, that I can rewrite as -3 times x to the 1/2, which I agree, you can do that. And then they say, okay, this right here is like x to the first power. And then this one, I think you can take the antiderivative of 7 pretty easily. What's the antiderivative of 7? Forget the negative for now. 7x, right? Because the derivative of 7x would be 7. And then they say, all right, and on the bottom, well, I can take the antiderivative of that. So what they wind up doing is they just take the antiderivative of everything, and that's their answer. And that's incorrect, because you have a quotient here. And we already know that in Cal 1, when you took the derivative of a quotient, it was a mess, right? It wasn't just take derivative of top and bottom separate, you just do them both separately. No, you had to do all that formula. So when you're undoing it, it's the same kind of disaster. However, I wrote this just special for you, and I intentionally made it so that the denominator had a single term in it. See, the denominator just has x squared. Why is that important? What's that going to allow me to do here? It's going to allow me to split it up into 3 separate fractions. That's the key to you being able to do this. You have to be able to recognize that you can rewrite this as -3 root x over x squared plus 5x over x squared, and then minus 7 over x squared. So you might be asking yourself, like, what is that step? Like, why am I doing that? What's going on? Well, remember that when we add and subtract fractions, you have to have the same denominator? Okay, so all I did was basically reversed it. Okay, I reversed it. Had I given you this and asked you to put it together, you would go to this. But in order to use the formula, I have to rip it back apart to this. And then for each of those, I can figure out what my x's are. So this is going to be -3 x to the half over x squared plus, well, can I just write 5 over x on this one? Because that one, I think, cleans up a lot easier, yes? And then minus, let's go 7. How about x to the -2 on that last one? We're almost to the point where we can use the rule. We just have to figure out what to do here. And that's just property of exponents, isn't it? Something to a power over something to a power, you subtract the powers, right? So I'm going to do 1/2, and I'm going to subtract 2. I'm not taking a derivative. I'm just using properties of exponents. So what is that going to be? What do you get when you take 1/2 and subtract 2? Negative what? -3 halves. So how am I going to write this? X, I just go x to the -3 halves, just like that? Yes, that's exactly what we do. I mean, you don't, because it's negative, yes, you could put it on the bottom, but then it would have to be positive, right? The answer, whatever it is always going to appear on top, even if it's a negative exponent. And then the rest of this, now, should I bring this up as x to the -1? I could, right? I could bring that up. However, I'm going to look at it like this because I already know that whenever I see 1 over x, just 1 over x, not 1 over x squared, not 1 over root x, just 1 over x, I already know the antiderivative of that's natural log. That's that special case, right? So I'm not going to bother writing it as -1, x to the -1. Now, -2, yes, because the formula will work for this one. All right, we're there. Why don't you take a few seconds to see if you can come up with the result on that. While you're working it, I'm just going to write it out here. Right, that should be it right there. Is everybody with me on this? Okay. Now, if you were to maybe look at the back of the book for an answer on a problem like this, you might see this. So they may prefer to not leave the negative exponents and drop that down on the bottom, and then x to the half is really root x. And then here, x to the negative 1, drop it down. And I'm just telling you, look, this is correct. This is 100% correct. Just because they use some properties doesn't make this more correct, all right? All right. How do you feel about that? All right? Okay, well, let's do one more. I said we were going to do two, but we're going to do this one. I want to see what people do with this one. This is such a fun problem. May I erase this, or do I need to keep this up? Erase, yes? Anybody see something fundamentally different between this problem and the one we did before? Yeah, you have two terms on the bottom instead of one. Had that been just x squared, I could split this into two pieces again, I'd be in business. But because there's two terms, it wouldn't work out as nice. Now, could I do this? Could I write? Like, is that algebraically the same thing? It is, right? They have the same denominator. If I put them together, I get 2 plus x squared over 1 plus x squared. That's this. But see, you can't use those rules here because you have two terms. You can't just like reduce the x's out. So it's not quite. All right. Maybe I should have left that up there. I don't know. What do you think? Anyone see what we might be able to do? How do you mean? That's if it was minus. If this was minus, we could factor it. But it's sum of squares, so we can't. Wait, multiply the top and bottom by what? By 1 over x squared. Is that what you said? Okay, so let's just see what would happen. I'm gonna do that because it's a fair move. This is being suggested. Don't write this down. Let's just see what happens. Okay, am I allowed to do that, everyone? Yeah, that's basically 1 over x squared over 1 over x squared is still like 1, right? So long as x is not 0, we can do this. And what would happen? Let's see, we go here to here, you get 2 over x squared. And then plus, when you do this to this, you get 1. And then here to here, you get 1 over x squared. And then here to here, you get 1, right? Does that help? Did we gain anything there? Does that make the problem doable now? What do you think? It was your suggestion, right? Yeah. Okay, so part of this class, trust me, as you'll see, if you truly are learning this for the first time, you are going to fail more times than you succeed doing your homework. You're going to do problems, you're going to fail, and you're going to have to crumble up your work and start over. Okay? It's going to happen more times than you're going to get it right. All right? So if you're at home and you're trying this, you try this. This is a legal move. Algebraically, you're allowed to do that. But you now need to recognize whether or not you've made the problem better. Or is it the same or is it worse? I look at that. I still can't split it up, right? I still can't break it apart. So I'm not quite sure I gained a lot with that. So maybe we crumble and try something new. Yes? Who else has a suggestion? Wait, what? The bottom what? Say yours, what? The bottom is, oh, okay, so you're seeing that This right here is the derivative of arctangent, right? So the antiderivative of this is arctangent, right? The antiderivative of this is arctangent. And you see 1 plus x squared here? Only issue is you got a 2 plus x squared up there. But the fact that you see that, that's important. That's actually part of how we can get to this. Does everyone see that now? Okay. Now how, though? How do we use it? Because the formula only works if you have a 1 up here. Okay. Oh, yeah. I know what you're saying. Any of y'all ever play sports when you were younger or still play sports? I remember I played baseball, all right? And I hated it. I absolutely hated it, okay? I loved basketball. I loved football. Baseball I hated. And one of the reasons I hated it is because I was a left-hander. And, you know, pitchers are really bad when they're young, and they get so used to pitching to right-handers. And then I get up there and I always got hit by the ball, which just wasn't fun for me. But the point I'm saying this, the reason I'm bringing this story up is because, like, I still got up and I had to go up there and, you know, take a swing. You know, like, and that's in this class, you have to still show up and take a swing. If you're not willing to take a swing, like, you're not going to ever progress in this. You have to make the mistakes. Or I don't want to say that what you said was a mistake. It's not a mistake if it's, yeah, you know what I'm saying though, right? You have to be willing to be wrong in order to get better at this. So, I'm okay with that. But it's a product now. And if we try, right now you may think, look, let's just go with what we think maybe it could be. Maybe capital F of x is just arctangent x, because that's the antiderivative of this, right? Times, and now isn't this just two little things I can take antiderivatives of? Like, wouldn't that be just like 2x plus 1/3 x cubed? Do you see what I just did? Okay? So maybe it is. All right, well, how do we check? Take the derivative of this, right? So let's take derivative of this. It's a product rule, right? So when you take derivative of this, what do you get? 1 over 1 plus x squared. Yes! Yes, I see it. Times just this, right? Okay, I don't see that anywhere over there. Plus, now the derivative of this, right? Which is 2 plus x squared. I see it. Times, crap, arctangent x. It's not over there, right? This has pieces of what we want, but it has things that we don't even have over here, right? So what you're splitting it up is good because you see something you recognize. The problem is undoing the product is not as simple as just doing antiderivative of each one. So that doesn't work. If you take your first test and you do this, that's like minus 9 out of 10. Because that is that's like you doing, in Cal 1, it's like you doing a product rule by just taking derivative of each one. That's what that's like in this class, going backwards. It's a big mistake. Okay. Still no go. You ready to see it? Anyone else have an idea? Say what? Do what with this?
Multiply by 1 minus x squared.
Oh, the like the conjugate type thing, like multiply the top. So you want to come in here and introduce an even crazier thing than the 1 over x squared. You want to come in here and go with 1 minus x squared, 1 minus x squared? Okay, I'm with you. Let's go with it. All right, so on the top, I would have to do this, right? Multiply this all out. 2 minus 2x squared plus x squared minus x cubed. Now, I could handle that if what turns out on the bottom is a single term, right? If it was just like something with x, I would be in business because I could split it up, but it's not. It's what? 1 minus x to the 4th, right? Because if you FOIL this out, do that, your middle terms cancel, but you still have the first and last terms. So you're still not there. Yes? Okay. I don't know. Maybe we can't do it. So I don't know if I stress this. I have 2 Calculus 2 classes. So I may say things to y'all that I thought I said to the other class, and I may, so y'all just tell me if I'm repeating myself. I think I told you all that this class, that there's got to be like instinct, like some sort of like instinctual type thing that is hard to teach. And the moves are very unnatural. They're not things that like product rule, very mechanical. So just check this out. This is such a beautiful solution to this. Watch. Just tell me if you agree with this. Now this is not the only way to do it, but do you agree with that? Yes? Okay. Now tell me if you agree with this. Do you see that? They have the same denominator, don't they? So if I put them together, I would get this, right? So what I did is I really split that into 2 pieces, didn't I? But I split it here. I didn't go into 3 different pieces. I went into the 1 over the denominator, and then the 1 plus x squared over the denominator. And do you see what the second term is? That's just 1. So this is now 1 over 1 plus x squared plus 1. 2 terms separated by addition. Right? And do you know the antiderivative of this? Arctangent x. Do you know the antiderivative of 1? Just x. So capital F of x should be arctangent x plus c. Wasn't that kind of nifty? Now, let's say you're sitting there, you're thinking, I never would have seen that. Well, now you have, right? And now you know that things like that can come into play, right? Nothing is off the table here. Any sort of algebra that you can think of, you can do. Now, if you didn't do that, there is another way to do it. Let's see how long it takes you to tell me what I'm doing. Long division. I could have done this. I could have done that. That's the original expression, isn't it? Now I wrote the x squared plus 2 in descending order, highest power down. So if you need to remember how to do long division. We're going to have to do it in here later on. So to do this, I have to see, what do you multiply this by to get this? 1. Okay, and then you multiply 1 times this, you get x squared plus 1. But then you have to subtract, right? So minus here, and then you go down. So nothing, and then you get 1 here, right? Then you say, okay, what do I need to multiply this to get 1? You say, oh, I can't. So I say plus, and then I put the remainder over the divisor. And that is exactly this expression, right? So you could have gotten this with long division also, but it's longer, right? That's just super clever. All right. I'm going to move on. You'll have plenty to practice in your homework. Okay, recall that when I put recall up there, that means you should have seen this in Cal 1 or pre-Cal or college algebra or somewhere in your life. If this is time and this is distance, and we have a function in here, which we'll use this function. We're not calling it f of x, we're going to call it s of t. S of t. T being time, and s, that's just the variable the book uses, all right? This function tells you where an object is at a point in time, right? So maybe like after 1 hour, this gives you some distance like 3 miles or something, right? But it's time and distance on the x and y axes respectively. Then from Cal 1, do you remember what the derivative of this function would give you? Not velocity. So if we take the derivative of this function, we get a new function, right? So this is your position function. That's what we call this, position function. But now, if we take its derivative and graph the derivative, s prime of t, it's not distance in time anymore. It's velocity in time. So if someone tells you where something is at every point in time, you take its derivative, and then you can tell somebody what the speed is or the velocity is at any point in time. Does that seem familiar from Cal 1? And then what if I do another derivative? You get acceleration. So here's time, and here's acceleration. I'll just put accel. And this right here would be s double prime of t. So this is called the velocity function. And this is called the acceleration function. Okay, y'all good? Now we have special notations for the velocity and acceleration functions. Instead of calling it like s prime of t, we call it v of t for velocity. And this one over here, we call it a of t. I thought I saw a hand, no? Okay. So we have this relationship from Cal 1. And it's, I think this is kind of interesting because if you think about it, what this is saying is that if somebody tells you where an object is at every point in time, exactly where it is at every point in time, does it seem reasonable that from that you could determine its speed at every point in time? And then from that you could get the acceleration at every point in time? Yes? Does it seem reasonable that it would work the other way though? Like if I told you, look, the acceleration of an object at every point in time is given, do you think you could go all the way back to tell me exactly where it is at every point in time? What do you think it would take to go from here to here? What would we need to do? Find the antiderivative. But what's the problem with the antiderivative? You get a plus c, don't you? It's a family of functions, right? And then if we went again, it's a family of functions. We lose information going backwards. Going this direction, we don't lose information, right? The derivative of this function is only one function, and the derivative of that function is only one function. So we have everything we need. But every time we try and go backwards, we lose something, right? So we need more than just the acceleration function given to us if we ever want to go back and get something's position, right? So let's get into that. I just wanted you to see, like, what we're interested now in doing is going that way. Now, before